Hello everyone. The topic of the lecture is asymptotics. So in this lecture basically we are trying to extend the notion of sequential limits to the sequence of random variables. So the basic idea is we have a sequence of random variables x1, x2, xn, and we are trying to understand the limiting behavior of these random variables as n goes to infinity. So in doing so, we are using several concepts. There are four concepts of convergence that we are using while dealing with the sequence of random variables. The first one is almost sure convergence. Second one is convergence in probability. Third one is mean square convergence, and fourth one is convergence in distribution. In this course, we're going to talk about only two of them, namely convergence in probability and convergence in distribution. So the definition of convergence in probability is given in definition 6.1. We say that the sequence of random variables xn converges to the random variable x if the limit of this probability that the absolute distance between xn and x is greater than epsilon goes to 0 as n goes to infinity. Okay. Usually we are using this notation as a shorthand notation for convergence and probability, or this notation. So once you have convergence and probability, then you can apply the definition of limits, because in the end of the day you are dealing with limits, right? So kind of the concept of limit is kind of universal. So you can apply the limit definition and get all other properties. Okay, these four properties. We're going to use some of those properties while solving examples. So basically, the first one is if xn and yn are convergent sequences of random variables, then their summation is also converging in probability to the sum of the limiting, let's say, quantities. Here the limiting quantities, I mean the notion is not really correct, because the limiting things of the boundaries, let's say the limits of the sequence of random variables may be random variables and some fixed values. So therefore it's not really a proper notion to say that when random variables are converging to their limiting point. That definition is not really precise. But remember that this convergence in probability can happen with regards to another random variable or some fixed value. Okay. Here we have one important theorem, that is weak law of large numbers. The idea is that the sample means the mean, the sample mean is converging to the true population mean in probability as n goes to infinity. Okay, so to prove this, we have to use the well-known Chebyshev inequality, okay, given here. So what we say is, we say that according to Chebyshev, we say that the probability that x minus mu is greater than some epsilon, that is going to be less than variance of x over epsilon square, right? So in this particular example, our proposition is that xn, so probability limit as n goes to infinity, the probability that xn bar minus mu is some positive epsilon distance, at least some positive epsilon distance from each other, is actually equal to 0. This is what we want to prove. This is the proposition or the theorem. Okay, then using the Chebyshev inequality, we can say that this limit should actually be less than variance of x bar n or epsilon square. Here I just use the Chebyshev theorem and apply limits to both sides of the inequality. Now the problem here is we don't know the variance of x bar n, whereas epsilon is some positive quantity that is somehow known. It can be an arbitrary positive, small positive quantity. So the most interesting thing, unknown thing here, is the variance of x bar n. But it turns out that it's easy to compute by just replacing the x bar n with its definition. So we know that x bar n is nothing but arithmetic mean of xi's in our sample, right? And given that we have IID assumption, independent and identical distribution of x's, given that x's are IID, then I can rewrite it as 1 over n square using the property of the variance times I goes from 1 to n sigma square of x, because of identity and independence. Actually, because of identity, we say that variance of x's are the same, they don't change, so all of them are equal to sigma square x, and we are summing the constant value. Variance of x is basically constant, that is what we assume, and summing a constant value n times gives us n times that constant value divided by n square, and then we receive sigma square x over n, right? So now let's replace it here in the right hand side of the Chebyshev inequality. Okay, we can say that this limit as n goes to infinity, probability of x bar n differs from the mean at least by epsilon, a positive epsilon distance, should always be less than the limit as n goes to infinity sigma square x over n times epsilon square. So obviously this right limit is equal to 0 as n goes to infinity, given that sigma square x is less than infinity, so it's finite, and epsilon is some arbitrary positive value. Okay, so that is basically completing the proof of this theorem. Okay, so this is really important result. This is called weak law of large numbers. You see, once you have the fact that x bar n approaches to mu in probability, if you have this convergence, you can go further and apply the same notion to sum of xi square over n. I goes from 1 to n, right? And you can say that this is gonna, I mean, in the end of the day, this is, you know, given that I can write yi as xi square, so in the end of the day, this is the mean of, I mean, the sample mean of another random variable, right? And I know that in the end of the day, it is going to converge to the expectation of yi, right? And it turns out that the expectation of xi square is, I mean, expectation of yi is nothing but expectation of xi square, which is sigma square plus mu square. So variance plus mu square, because remember the definition of the variance, we said that variance of x is actually equal to expectation of xi square minus expectation of expectation of x square minus expectation of x's, square. So basically you can leave expectation of x square in the left hand side, and you will receive that expectation of x square is nothing but equal to sigma square x plus mu square of x, right? So this is really a useful result. It tells you that the sample statistics, they will converge in probability to their population analogs given some regularity conditions. Okay, and that regularity condition is mainly about the IID. Okay, and we have some other properties that we talked about. Maybe I have to mention them because we're going to use it. We said that if you have xn converging to some x in probability, right, and if you have some continuous function g of xn, okay, that continuous function, this basically, the left side implies the right side. The right side is basically tells you that g of xn is going to converge in probability g of x given xn converges to x in probability. Okay, so we're going to use this fact here. We have x bar. We know that x bar is basically x bar n is nothing but summation of xi over n, right? We know that it converges to the expectation of x, or in another notation mu, yes? So if this is the case, then it turns out that x bar square and should also converge in probability to mu square. Okay, we're going to use these two results. So remember this one. We said that expectation of xi, we said that xi square over n, sum of xi square over n, converges to mu square or mu square plus sigma square, right? So let me rewrite it. We said that this is going to converge to mu square over sigma square. This is the first result. And then using, this is actually called continuous mapping theorem, the fact that if g is a continuous function and if xn converges to x in probability, then gxn converges in probability to gx. This is called continuous mapping theorem. Okay, so these two results given in red rectangles will be used in further examples. Remember that. Okay, let's move on. We have proven the weak law of large numbers. Now what we have to do is we have to show that the sample variance, the formula of which is given here, is a consistent estimator of the true population variance. When we say that we have a consistent estimator, we mean that the estimator is converging to the expectation in probability. So basically, this is what we mean. If xn bar is the sample mean, for example, and if it converges to the true population mean in probability, we say that x bar n is a consistent estimator of the population mean. Okay. So here we go. Let's erase it. Okay. Good. So Sn square is the xi minus x bar square over n minus 1. Then we can rewrite it as sum going from 1 to n xi square minus x bar times sum from 1 to n xi plus, and here we have 2 obviously, plus sum I goes from 1 to n x bar square over n minus 1, and we can simplify it in this way. So remember that x bar is nothing but sum of xi over n. This implies that sum of xi is nothing but x bar times n, right? And also we have to mention some other property. We know that if you are summing some constant value, in this case x bar square is a constant value, obviously, that is nothing but n times that constant value. So basically we get rid of the summation symbol using these two properties. So let's simplify the equation here. Sum of xi square, I goes from 1 to n times minus 2 times, instead of sum of xi here, look at it please. So instead of sum of xi here, I will write n times x bar, and then I will receive x bar times, just a second, so x bar times x bar times n. So this guy is actually sum of xi from 1 to n, right? So that gives me what? That gives me 2n x bar square. So 2n x bar square, and plus here I have sum of x bar square. I can rewrite it as n times x bar square, okay, and divide by n minus 1. Great. And then we can simplify it further, because we see that these two guys are have the same terms. We can rewrite it as sum of xi square, I goes from 1 to n minus n times x bar square over n minus 1. and I will rewrite it in this way: 1 over n minus 1 times sum of xi square. I goes from 1 to n minus n times x bar square, right? So now we know that if we divide these two terms, pay attention to the terms within the parentheses. So if we divide it by n, if we divide this guy by n, the first guy by n, and the second guy by n, we will have two converging things. We know that x bar is going to converge. So let me divide by n. Oops. And divide this part by n. But if I divide the inside of parentheses by n, I have to multiply by n, right? I can multiply and divide by n, so the equality will still hold, right? Why I do that? Because I know this term. I know that this term will converge in probability to mu square plus sigma square, and this term, if I divide by n, this term is just x bar square, and that is going to converge to mu square, right? So let's keep it as it is, and then we know that we can use this property here. The fourth property is telling you that if you have two converging sequences in probability, right, then their product, the product of those sequences of random variables obviously, will be equal to product of their limits as n goes to infinity, obviously, right? So here I have the limit of this guy, I have the probability limit of this guy, but I don't know this guy here. But pay attention, if as n goes to infinity, this guy is going to converge to 1, right? So just using the fourth property that I have mentioned, you know, when you have the product of two, let's say, sequences of random variables, then their product will converge in probability to the product of their limits, right? So I can say that this guy here is going to converge to 1 times this guy here is going to converge to mu square plus sigma square, and this guy here is going to converge to mu square, so minus mu square, and in the end I will receive sigma square. So what we got here is we got the fact that the sample variance is actually converging to true population variance as n goes to infinity, or you can say sample variance converges to population variance in probability. Okay, so we have done this. What else? Yeah, convergence and distribution. This is the second type of convergence. Basically, we have suppose we have x1, x2, and xn. Now we are interested in the limiting distribution of this sequence of random variables. Okay, so previously we were interested in the limiting value, let's say, right, in limiting, let's say, random variable or limiting point, but here we are interested in the limiting distribution. So what happens to the CDF of xn as n goes to infinity? So it turns out that if there is a limit, if such a limit exists, that CDF of xn gets equal to CDF of x as n goes to infinity, then we say that xn converges to x in distribution. You see we have written t here on the top of this right arrow, showing that we are talking about convergence and distribution. So xn converges to x in distribution. Okay, we have the same continuous mapping theorem result for convergence in distribution. And you have to know that if you have convergence in probability, that automatically implies convergence in distribution. And third, we have, if you have, you say, a linear transformation of random variables, some linear combination of random, let's say, vectors or random variables, and given that each of them has some, limiting distribution, then the overall sequence, the linear combination of those sequences, will converge to A plus Bx in distribution. Okay, one of the most important examples of convergence in distribution is the central limit theorem. It basically tells you that if you have IID sequence of random variables with finite mean and finite variance, in that case, the sample mean, the average of this, sequence will converge to, its distribution, its limiting distribution will be normal distribution. Here we have some, let's say, linear combination of x bar n, but this is one form, one notation for central limit theorem. We can also rewrite it, as an implication of this thing in the red rectangle. We can rewrite the distribution, asymptotic distribution of x bar, saying that this is asymptotically normally distributed with mean equal to mu, with variance equal to sigma square over n. So these two things are actually equivalent things. Here we are talking about these random variables distribution, but in the second one we are talking about x bar n's distribution. The advantage of central limit theorem, the power of the central limit theorem, lies in the fact that it does not make any distributional assumption on the axis, and that is really powerful. Now let's solve one example. In example 2, we have xi, which is Bernoulli random variable. Actually, we have a sequence, and each x has probability of success equal to 25%. We have to use normal approximation to find given probability given n is equal to 100. Now, to solve these kind of questions, the first thing that we have to do is we have kind of find the limiting distribution of x bar. This is the final thing, right? This is the random variable of interest for us. According to the central limit theorem, this notation, this version of this, let's say, central limit theorem, I have to use a blue rectangle to put it within the blue rectangle here. So we can say that if each x is Bernoulli with probability of success equal to 25%, then x bar n has a limiting distribution which is normal with mean equal to p, yes, expectation of x, right, which is 0.25, with variance equal to 0.25 times. We know that Bernoulli distribution has p times 1 minus p as its variance, and we have to divide it by n, which is 100. Now that's cool, because we already have the distribution of the random variable, which interests us. Now it's a piece of cake to find this probability, because x bar, we know that x bar has a limiting distribution which is normal, and we know how to find the probability involving normal distribution. So here we have to find probability of x bar n, or x bar, better to write x bar n actually is less than or equal to 0.2. Okay, so given that x bar n is normal, at least asymptotically, we can convert it to standard normal, yes, using the Z transformation. So we can say that instead of finding probability of x bar being less than or equal to 0.2, I can find probability of Z, random variable, standard normal variable, less than or equal to 0.2. Now let's perform the Z transformation. Z score is going to be 0.2 minus mean, which is 0.25, divided by the standard deviation, which is square root of 0.25 times 0.75 or 100. Yes. Now, finding this probability should not be a problem. You can check. You have to calculate these things and check the Z table, or you may have a calculator where it is easy to find the areas under the standard normal distribution. So the rest is not going to be solved here. You can find it by yourself, I hope. Okay, so basic idea is that just find the limiting distribution, and that's all. You don't really care about the distribution of x's. Okay, we don't even need this information. Given that we know the mean and variance, we don't really need this information, that it is Bernoulli random variable. This is some kind of extra information here. Actually, to give us information about, you know, this was actually mentioned here so that we could infer the mean and variance of x bar n. Yes, but in general, you don't really need any distributional assumption. Now we have some extension of the central limit theorem. It basically tells you that if you have you say some xn, obviously if you have xn with finite mean and variance, it's obviously going to be asymptotically normally distributed. You see, its limiting distribution is normal with mean 0 and with variance sigma square. It is basically restating the central limit theorem, but the delta method is telling you that if you have some gx, continuous and differentiable function, at theta, here theta is obviously the mean, at least, yeah, when you're talking about the central limit theorem, yes. Yeah, it may be something else, but so if you have a differentiable function g, which is differentiable at this theta here, and given that the derivative of g at theta is not equal to 0, then g of this guy minus g of this guy is going to be asymptotically normally distributed with mean equal to 0, with variance equal to this strange guy. I can rewrite it because usually what we need is, we don't really need the asymptotic distribution of the whole thing. As we did for central limit theorem, we said that x bar, x bar is actually is the random variable which interests us, right? So we don't really care about, sometimes we don't really care about the distribution of the whole thing, but we care about the asymptotic distribution of x bar n. So we said that if this is the case, then x bar n is going to be asymptotic normal with mean mu and with variance equal to sigma square over n, right? So we can do the same thing here. This is just alternative notation, alternative specification of the delta method. We can say that g of x bar n, or xn here, doesn't matter, is going to be asymptotically normally distributed with mean equal to g of theta and with variance equal to sigma square times g dash of theta square over n. Okay. Good. Now let's look at some examples here. We have xi, example 3. We have xi, which is normal IID distributed with mean 2 and with variance 1. Now we have another random variable y, which is equal to x bar square, right? And if this is the case, we can apply, we can apply the delta method to receive the distribution for y. We know that x bar is going to be, x bar n is going to be normal. In this case, because we have normal distribution for x's, for sure we're going to have normal distribution for x bars, because if you remember, we got a theorem telling that linear combination of normal variables is still normal. So basically we don't need to write d here, asymptotic distribution, because x's here, they are normal, NIID, so they're normal and identically and independently distributed. So therefore we don't really need that d here. X bar n will certainly be normally distributed, but the mean of it is going to be 2, but the variance is going to be 1 over n, and n is 100 here. Okay, keep that in mind. Now let's apply the same logic. We can say that if this is the case, maybe I have to write the alternative version of this central limit theorem, which tells us that xn minus 2 over 1 over square root of n, just a second, actually, square root of n times this guy is going to be normal with mean equal to 0, with variance equal to 1, right? And now we are applying the gx. Gx is actually the square function, right? We're applying g on each term. We're applying g on this guy and g on this guy, right? We can say that if this is the case, square root of n times g of x bar n is going to be x bar square minus the square of 2 is 4. That is going to be normal. Mean is going to be 0, and variance is going to be equal to the variance of x n, the variance, the all variance times g dash of theta. The theta's derivative is going to be, so the y dash is nothing but 2 times x bar, right? And if you evaluate it at theta corresponds to 2 here, right? So it's going to be 1 times 2 times 2 squared, isn't it? Okay, so 1 times the derivative of this function evaluated at theta, and the value of theta is equal to 2 here, right? So maybe we have to go back and recheck the theorem, right? So variance times the derivative of the function evaluated at theta, and square everything in the end. So this guy gives us 16 here, right? So it's 16. Good. We can rewrite it as, you see, we can say that we are interested in not in the distribution of the whole thing, but in the distribution of x bar n's squares distribution. So we can use the alternative version of the theorem, central limit theorem. We can say that x bar square is going to be normal with mean equal to 4. Yes, this guy here, this 4 comes to here, and 16 over 100. Yes, so square root of n becomes n when you move it to the right side. So n is equal to 100. So basically, this is the distribution of x bar square, or you can say the distribution of y. Right? Now it's easy to get the probability, given that we have normal distribution, right? We have normal distribution, and it's really easy to get the probability that y is less than or equal to 3.7. We know that instead of this probability, we can calculate the probability of z less than or equal to 3.7 minus 4 divided by square root of 16 over 100, yes, which is actually 4 over 10. So let me write 0.4, right? It's 0.4, and that is nothing but probability that z is less than or equal to minus 0.3 over 0.4, which is probability that z is less than or equal to minus 0.75, I believe, right? And the rest is easy. You can check the table and find what this probability is equal to. So I'm just skipping that. Now let's look at the next question. The next example is about a sequence xt, which is defined as epsilon t plus epsilon t minus 1, given that epsilon t and epsilon t minus 1, both of them are IID with 0 and 1, with 0 mean and variance 1. Remember, IID is necessary and sufficient condition to apply the central limit theorem. Okay, we don't really need any other distributional assumption on the particles of xt here. IID is basically enough, and given that we have mean and variance, given that we have finite mean and finite variance. So the first thing that we have to prove, we have to show that we have convergence of this, you say, x bar n is going to be converging to 0 in probability. So remember, we have shown that whenever you have x bar n, yes, the average of the sequence values, the average of the arithmetic average of the random variable values in the sequence, this is converging to the expectation of x all the time based on the law of large numbers, right? Given you have IID assumption, and based on the law of large numbers, this guy is going to hold. So here, what is the xn? Xn is nothing but, xn bar is nothing but x1 plus x2 plus xn over n, right? And each xn, each x here, x1, x2, they are actually compositions of, so this is actually e1 plus e0, yes? So this is x1 plus, so xn is nothing but epsilon n plus epsilon n minus 1, right? Divided by n. Good. So what we have to do is we basically have to find the expectation of x. If expectation of x is equal to 0, then we are sure, for sure, the x bar n is going to converge to 0. Yeah, the law of large numbers tells you that whenever you have IID assumption, x bar n will converge to expectation of x in probability. So what we have to do is we just have to find the right hand side of this thing. If the right hand side is equal to 0, then we are okay based on the law of large numbers. So what is expectation of xt here for any arbitrary t? This is, just use the substitution. Instead of xt, we are going to plug epsilon t plus epsilon t minus 1, and because expectation is a linear operator, I can split these two things, I can say that this is equal to expectation of expectation of epsilon t plus expectation of epsilon t minus 1, which is 0 by definition. You see, by definition we have IID with mean 0 and with variance 1, so basically we got 0 for expectation of xt, and by law of large numbers we know that x bar n should always converge to expectation of xt here in this case, which is equal to 0. So a part is kind of done. Now let's move to the second part of the question. Second part is telling you that we have to apply the central limit theorem and find the we have to find the asymptotic variance of x bar n. So again, x bar n is nothing but x1 plus x2 plus xn over n, which is equal to, so instead of x1 we can plug epsilon 1 plus epsilon 0 plus, instead of xn we can plug epsilon n plus epsilon n minus 1, right, divided by n. And if you want to find the variance of x bar n, that is nothing but, here actually we just need to find the variance of x, not variance of x bar, but let's find the variance of x bar n. So variance of x bar n is nothing but variance of all these things, yes, sum of variances of all these things. And it turns out that, so this is n times variance of xt, yeah, t goes from let's say 1 to n, so just a second, I made a mistake. So let's use the central limit theorem, this version of the central limit theorem. We say that square root of n times x bar n minus mu, which was 0 in our case, so that we just deleted. This is going to be asymptotically normally distributed with mean 0 and with variance equal to the variance of x. And here we have, instead of x, we have xt. So basically we have to find the variance of xt, which is equal to variance of epsilon t plus epsilon t minus 1, which is equal to, because of IID assumption, remember that because of IID assumption, this is nothing but variance of epsilon t plus variance of epsilon t minus 1. Here we have covariances equal to 0 because of independence, and because of identity we know that the variance of this guy is going to be equal to variance of this guy, and by definition each of them has variance equal to 1. So in the end the variance of xt is equal to 2, and because here we need the variance of, see, here we needed just the variance of xt, just replace for variance of xt, which is equal to 2. What we can do is we can also say that let's use the other version of the central limit theorem. We can say that x bar n is asymptotically normally distributed. You can write this tilde, or you can use the right arrow, with mean equal to 0 and with variance equal to 2 over n. This is an alternative version. I mean, they are equivalent basically. Now let's look at example 5. In example 5 we have two random variables, x bar 1 and x bar 2, So assume you and your friend, you're flipping coins simultaneously. So this is your first coin flip, this is your second coin flip. So you are the first guy, therefore I have superscript 1 for you, and then you basically flip the fair coin n times, and the same is done by your friend, which is the second guy, simultaneously. Yeah, so you and your friend, you are flipping a fair coin simultaneously, and obviously xi is Bernoulli here with probability of success equal to 0.5, right? So what else? Yeah, we have to use an approximation for the probability that x bar 1 minus x bar 2 is less than 0.1 is equal to 0.95. So basically we are searching for n, for the sample size for which this probability is going to be exactly equal to 0.95. So what we can do is we have to define this as, we can create a new variable y, which is just the difference between averages of these two random variables, and find the distribution, asymptotic distribution for this new random variable, you see, and then this probability is going to be a piece of cake, right? So let's first find the asymptotic distribution of x bar 1. We know that x bar 1 is going to be approximately normal with mean equal to 0.5, because that is the mean of the Bernoulli random variable, and the variance is going to be 0.5 times 0.5, which is 0.5 squared, divided by n, right? And the same is going to be the case for x bar 2. It's going to be approximately normal with mean equal to 0.5, with variance equal to 0.5 squared divided by n. Now let's find the distribution of the difference of these two random variables. So x bar 1 minus x bar 2, let me denote it as y. It's obviously going to be normal, at least asymptotically normal, because we know that the linear combination of normal random variables is still normal. So if x1 and x2 they are asymptotically normal, then their difference should also be asymptotically normal. So y is asymptotically normal. The mean is going to be equal to the difference between these two means. 0.5 minus 0.5 is just 0, and the variance is going to be, the variance of the difference is going to be equal to the summation of the two variances. So this is going to be 2 times 0.5 squared over n, right? Good. Now after finding it, we can say that probability that x1 bar minus x bar 2 is less than 0.1 can be rewritten as probability that absolute value of y is less than 0.1, but because y is normal variable, normally distributed, at least asymptotically, in that case we can rewrite it as probability. We can use like z transformation. We can say that this is z, probability that random variable z, standard normal random variable z is less than. Now let's apply the z transformation to the right side of this inequality. 0.1 minus 0 over square root of 2 times 0.5 square over n, right? And that is nothing but, so probability of z. Let me rewrite it in this way. I can say that this is equal to probability that minus 0.1 over, so 0.5 times square root of 2 is less than the random variable z, and that is less than positive 0.1 times square root of n over 0.5 times square root of 2. And by definition, we are searching for such a quantile of this standard normal distribution such that the overall probability is going to be exactly equal to 0.95. And we know that such a quantile, you can check the standard normal distribution table, such a quantile which gives us 95% probability, you see, this is minus z and positive z, like this, these are lowercase z's, quantiles, but this is capital Z. So that z is actually equal to 1.96, and the lower quantile is nothing but minus 1.96. Yes, so let me delete these guys. Yeah, the lower quantile is negative and the upper quantile is positive 1.96. Now what we can do is we just equate, either we can use this or this guy here. We can say that 1.96 is equal to 0.1 times square root of n over 0.5 times square root of 2. Yes, that means that square root of n is equal to 5 times 1.96 times square root of 2 over, okay, nothing here, it's just equal to 1.96 times 0.5, 5 times 5 times square root of 2. And if you square both sides, you receive n is equal to so approximately this is equal to 4 times 2 times 25, isn't it? Something like this. I hope I got it correctly. So this is arithmetics. This is up to you. Just find n from this equation, and that is your problem. Okay. So example 5. We have solved example 5, and then we have the multivariate version of the central limit theorem. I mean, nothing changes basically. The only difference is that you have vectors instead of random variables. You have random vectors here, and the idea is that if each element is just a second. First, we have convergence and probability for multivariate version. So you say that random vector xn converges to x vector x if each element of xn converges to each element of x. That is basically what it is saying. Now, theorem 6.8 is the multivariate generalization of the central limit theorem. Okay. So here, instead of a random variable x, you have random vector. Mu is also a vector. Yes, and here the sigma, capital sigma, is a variance covariance matrix. Okay, so that's all for today. See you in the next classes. Have a good luck.